Welcome, folks. A video on advanced applications of integrals. In this video, we're going to be talking about the basics of probability theory. So I'll give you a little bit of foundation. We'll talk about a couple different averages, and then we'll talk about an application to waiting time. Here's the foundation. When we talk about probability, we talk about the probability of some random event occurring. We say that the probability of that event is equal to little p, where p is always a number between 0 and 1. And our interpretation is that if p equals 0, the event is impossible. And if p equals 1, the event is certain. Generally speaking, these events can be drawn from either continuous or discrete distributions. Now, what that means for our purposes is not so important, but you can think of, for example, the event of getting a 7 when you roll 2 dice as being drawn from a discrete probability distribution, whereas the probability that a male weighs between 160 and 170 pounds is drawn from a continuous distribution. In this course, since we're talking about integrals, we're going to be talking about continuous distributions. Okay, so let's talk about a density function from a continuous distribution. If the function is non-negative and it has integral 1, there should be a dx here. We say that that function is a probability density function. And if the event, like I described before, is the probability that a man in the United States weighs between 160 and 170 pounds, the probability of that event is an integral. In this case, we'll take that event to be the probability of the random variable being between a and b. And again, the probability of that event is the integral from a to b of the probability density function. Okay, so we'll start off by talking about a specific type of a density function. And let's go ahead and determine a constant k such that this satisfies the requirements of being a probability density function. Again, a non-negative function whose integral is 1. In this case, we say that the integral from minus infinity to infinity of this function f of x can be evaluated, of course, since it's 0 from any of its values, by integrating from 0 to infinity of k e to the minus 3x. Of course, we'll write that as a limit of a well-defined definite integral. The limit as t goes to infinity of the integral from 0 to t. We can evaluate that using the fundamental theorem of calculus. And of course, as t goes to infinity, e to the minus 3t goes to 0, giving us the value here, k over 3. Again, our probability density function has to have integral 1, so we see that it had better be that k is equal to 1, k is equal to 3 for this to be a probability density function. Okay. Let's go ahead and talk about averages. When we talk about averages, usually we mean the arithmetic mean, and the arithmetic mean is sort of like the mean value of the distribution. When f is a probability density function, the mean value of that distribution is integral from minus infinity to infinity of x times f of x dx. You'll notice that this is a lot like the center of mass of that probability density function, and it exactly is. So here's an example. Let's go ahead and find the mean value of this distribution. Now, I've left off a lot of the details here, but we know that the mean value is given by the integral from minus infinity to infinity of x f of x dx. This, of course, can be expressed as the limit of a well-defined definite integral from 0 to t. There's integration by parts here to find this antiderivative. Of course, there's a L'Hopital rule to evaluate the limit as t goes to infinity. And at the end of the day, we end up with 1/3 for the value of the mean value of the distribution. Okay, a second type of average is called the median. The median is the special point in the distribution that divides the distribution in half. So it's the special value m such that integrating from minus infinity to m is 1/2 of the distribution. You'll recall that the integral over all real numbers, minus infinity to infinity, of a probability density function has to be 1. So integrating to m, the median value, exactly divides it in half. Okay, let's see an example here. Let's find the median value of the distribution described by this distribution we've been dealing with probability density function 3e to the minus 3x when x is non-negative. Here we see that the integral from minus infinity to m of the probability density function is the integral from 0 to m of, that should be a 3, of 3 e to the minus 3x dx, which at the end of the day, you end up with 1 minus e to the minus 3m. Now, we need that value to be equal to 1/2. Using properties of exponents and logarithms, we see that the median value of this distribution is the natural log of 2 divided by 3. Okay, let's go ahead and see an example of this distribution, this probability in action with waiting time. So it turns out that when you have to wait for a bus or when you have to wait on hold, that if you know the mean waiting time mu, that the wait times in a distribution come from probability density function f of t equals 1 over mu times e to the minus t over mu when t is non-negative. So we'll go ahead and just do a couple of things with this probability density function. Here's the first one. Let's find the probability that a customer waits less than 1 minute. So this is our event in this case, the probability that the amount of time on hold is less than 3 minutes. So we'll go ahead and have a look at an integral to identify this probability. So here we see that the probability that the wait time is less than 1 is integral from minus infinity to 1 of this probability density function. So we integrate from 0 to 1 of 1/3 e to the minus x over 3 dx, which ends up being 0.28, or about a 28% chance. Similarly, if the event is more than 5 minutes, we can evaluate a different integral. In this case, we see that the probability that the wait time is greater than 5 minutes is the integral from 5 to infinity of our probability density function. We can evaluate that again as the limit of a well-defined definite integral. And as b goes to infinity, in this case, we see that this exponential term goes to 0, giving us e to the minus 5/3, which is a 0.18, about an 18% chance. Lastly, let's go ahead and find the median wait time. We know that the median wait time is that special value m that divides the distribution in half. Here we see that that integral dividing the distribution as half is the integral from minus infinity to m of f of x dx, our distribution function, which simplifies as the integral from 0 to m of 1/3 e to the minus x over 3 dx. Of course, we can evaluate this quickly using the fundamental theorem of calculus as 1 minus e to the minus m over 3. In this case, with the value of that definite integral equal to 1/2, we again use properties of logarithms and exponents to see that the median wait time has to be 3 times the natural log of 2. So about half the people wait 2.08 minutes or less, and the other half of the people wait 2.08 minutes or more. Okay, folks, hope you've enjoyed this brief introduction to probability theory. Have a great day, and we'll see you next time. Bye-bye.